Good afternoon, everyone. Welcome to the second in a series of autumn webinars about the new climate adaptation and risk assessment tools that are hosted here on Oasis Hub and how they can help you. So with more frequent flooding, storms and extreme weather, your role, whether it be in insurance, municipalities or elsewhere, involves taking informed decisions about your climate risk assessment and adaptation and resilience strategies. And this includes analysis of current and future hazard and risk, climate change impacts, and the quantification of the damage and financial losses of a flood in a specific place. We understand that for many of you watching or being clear about what flood tool to use linked to your specific objectives isn't often an easy decision. So our webinars this autumn are aimed at helping you understand the types of tools that you could consider. We'll demonstrate how, by talking to the scientists and flood specialists themselves, like Ambiental Risk here today, talking to them about the state-of-the-art specialist flood tools. We'll show the diversity of the tools available to you and help you decide which types of tools work best for the challenges that you need to address. You can see the details of our other flood webinars that are coming up, and the one that you might have missed, I'll post the link in the chat box shortly. But today we're going to present a really exciting set of digital services provided by flood specialist Ambiental Risk, which can support you in addressing global flooding challenges and understanding how climate change is predicted to increase flood risk. We're about to see presentations of three separate services. The first from Katie Smith, who's a technical manager at Ambiental and a senior member of the flood modelling team, leading and instructing technicians in global flood map production and product development. She will present the European version of FloodScore, which provides consistent residential and commercial flood risk scores at a property level. Dr. David Martin will be up next. He's the Chief Technical Officer at Ambiental. He has extensive experience in the areas of flood risk modelling, geospatial systems and product development. He's going to present FloodFutures, which is a predictive flood model that considers 9 possible climate change scenarios between 2020 and 2080. And this is aiming to help insurers and reinsurers, utility companies, local authorities, infrastructure managers, commercial developers, and others understand and plan for long-term flood risk. Our last speaker will be Dr. Rubini Santha, who's a lead catastrophe modeler, a flood cat model developer, and an expert of LiDAR remote sensing for hazard mapping applications. They're going to present FloodCat, which are models which use historic river, rain, and tide gauge data to simulate potential future flooding disasters. So I'm going to take questions after the 3 presentations have been made, but please feel free to post them in the Q&A or chat boxes as we go along. And before we hear from the speakers, I'm going to hand over to Rob Carling from Ambiental Risk, who's going to give you a quick introduction to the company.
As Will said, I'm going to hand over to Katie Smith in a few minutes, just to on the European data, then David, then Rubini. Just really a little bit about Ambiental as well. There is a Scan Me code you'll see, and also we're offering an exclusive offer of a consultancy sort of to book a consultancy sort of review as well. So that will be at the end of the presentation, and as Will said, we'll take questions at the end. Just a really little bit, as Will introduced, these are the 3 speakers. Hope you can see the screen there, Katie Smith and David and Rubini. Really just a little bit about Ambiental. We're dating back to 2001, 2002. We're specialists in flood, particularly in the insurance and financial sector with the UK, European and globally. We have national scale sort of flood models. And some of our clients include the World Bank, the Space Application Agency, the Chubb Insurance, QBE, Zurich, and many, many more. We were recently taken over, well, probably 14 months or so ago now, by Royal Haskell and DHV, which is a global consultancy, Dutch consultancy, over 6,500 colleagues across the globe in over 30 countries. We're quality assured as well, so everything we do is quality assured and sort of tested. So with more to do, I'll just hand you over to Katie to start with, and I'll be back at the end to sort of go through a sort of wrap up as well. Thank you. Over to you, Katie.
Thank you very much, Rob. Yes, so as introduced by both William and Rob, my name is Katie Smith, and I'm the technical manager at Ambiental, having worked for the company for about 5 years now. But yeah, so today I'm going to talk to you about our EuroFlood program. So Rob, if you could go on to the first slide, please. Perfect. So our EuroFlood program comprises the development of a new suite of flood risk products, including FloodMap, FloodScore, FloodFutures, and FloodCat, which we are currently rolling out in countries across Europe. We have applied the same modelling techniques as those employed for our existing flood risk solutions in other territories throughout the world, thereby creating a globally consistent view of flood risk. Together, these products allow customers such as insurers, utility companies, local authorities and risk managers to understand and assess the current and future flood risk to their assets or exposures. Today, I'm going to focus on our EuroFlood, FloodMap and FloodScore products, with my colleagues presenting to you FloodFutures and FloodCat. So could we move on to the next slide, please, Rob? Thank you. So firstly, I wanted to provide an overview of how we approach flood modelling at Ambiental. So whenever we initiate a project in a new territory, we follow this process, which starts with a research phase and ends with a final flood hazard mapping product. One of the first steps is to conduct extensive research to gain an understanding of exactly what data and information is already available and how we might develop a flood model in this territory. We obtain this information from a range of sources, including government agencies, data suppliers, academic literature, media reports, and so on. Once this phase is complete, we then start to build our knowledge base of the various input data sets required to support the hydraulic modelling. Examples of these data sets include geospatial layers such as topography data, for example, digital terrain models or DTMs, gauge data, land cover data, and also information about defences, flood defences. The next stage involves the analysis and pre-processing of the numerous input data sets using GIS to enable that everything is in a correct and compatible format. So this process includes treating the data to remove artifacts that could potentially unrealistically impact the results of our hydraulic modelling, for example. And it can also include aligning the format and resolution of data sets from a range of different sources. Hydrological modelling is then performed to calculate the flood model input river flows, rainfall intensities, and tidal levels. And in the case of our EuroFlood products, we have used local hydrological methodologies and parameters within each country that we've modelled. So then moving on to the hydraulic modelling. So everything that has been processed and obtained up to this point is then used as inputs to the hydraulic modelling, which involves running hundreds of thousands of overlapping flood simulations, the outputs of which are combined to form our flood hazard maps. For EuroFlood, we used our own proprietary 2D flood modelling software to do this, FloodFutures. So then finally, once the flood hazard maps have been built, they are subject to rigorous quality assurance inspections, both automated and manual, in order to validate the modelled outputs. The flood maps are also regularly verified against real flood events, which are identified as part of the research phase. So if we could move on to the next slide, please, Rob. Thank you. So now I'd like to explain our EuroFlood flood map products in a bit more detail. So these products provide high precision flooding depths and extents at 5-metre resolution for a range of return periods from the 20-year up to the 10,000 year for multiple flood sources, including fluvial or river, pluvial or surface water, and tidal or coastal storm surge flooding. FloodMap is available at a national scale for countries in Europe, having been developed using a high-resolution pan-European DTM and our globally consistent modelling techniques, with the increased accuracy benefits of incorporating local sub-country hydrological parameters and methodologies. Ultimately, our FloodMap products provide customers with the ability to visualise, assess and understand flood hazard where it matters to them. And the image on the right-hand side there is just an extract of our Spain pluvial, so our Spain surface water flood map. So we can move on to the next slide, please, Rob. Thank you. So now I wanted to talk a little bit about our EuroFloodScore products. So these products provide flood risk ratings for all properties in European countries, covering both residential and commercial premises. Flood hazard depths are extracted from our flood map data to each individual address and combined with unique damage values to produce average annual losses, which are then scaled into flood scores of 0 up to 100. These risk ratings are also classified into bands from negligible up to very high and are consistent both within and between countries in Europe and beyond. For each individual property, a combined risk rating is provided in addition to individual scores for each flood source. So essentially, FloodScore gives a measure of the likelihood and severity of flood risk at the property level, and it also includes supplementary information such as the maximum flood depths for all modelled flood sources and return periods, and also other metrics are available, such as annual damage ratios, which are relevant to the insurance sector. And finally, the last thing I was going to say about FloodScore here was that it facilitates the screening of exposure portfolios and supports decision making by enabling risk thresholds to be established. For example, by deciding to only insure properties with a flood score up to 50. So that's how a lot of companies use our flood score data sets. Thank you, Rob. So yes, now moving on to the next slide, I just wanted to show you examples of some of the insights and comparisons that can be derived from our EuroFlood FloodScore databases. The first of which shows breakdowns of the percentage of properties at risk of any depth of flooding in Northern Ireland and the Republic of Ireland, firstly by region and then by flood source. So in terms of the proportion of total properties affected, the combined chart, which you can see on the right-hand side, shows us that both Northern Ireland and Republic of Ireland experience similar levels of risk. However, by looking at the other graphs, the data shows us that this risk is driven by different flood sources. In the Republic of Ireland, fluvial and tidal flooding affect the greatest number of properties, whereas in Northern Ireland, pluvial is the dominant source of flooding. In fact, according to the Department of Infrastructure's flood risk assessment, Northern Ireland is actually estimated to have aggregated annual average damages of £56 million, 74% of this actually being attributed to pluvial flooding. Next slide, please, Rob. Thank you. So in contrast to the previous slide, which looked only at the amount of properties affected by any level of flooding, these charts represent the distribution of flood score risk ratings between very low and very high, and therefore include estimations of likely damage. So overall, half the properties within these risk bands in Northern Ireland are classified as having very low flood risk. And although we can see that the majority of properties affected specifically by pluvial flooding are calculated as having very low risk, there are many more properties affected in absolute terms, which is why it is the most dominant flood risk in this region. And on to the next slide, please, Rob. Yes, so this is just a final example, but this time focusing specifically on pluvial flooding across Spain, Portugal and France. So in terms of the proportion of total properties affected by pluvial flooding in each country, Spain is shown to experience the highest, while Portugal experiences the lowest. These graphs also show us the distribution of risk within our FloodScore risk rating categories. And it shows us that it's very similar actually for each country. And the reason I wanted to show this was that our FloodScore databases from different countries can be compared directly because we've used the same modeling and approaches. And also our risk ratings are truly linear. So therefore, a score of 50 is exactly half the risk of a score of 100. On to the next slide, please, Rob. Thank you. Yes, so finally, I just wanted to discuss and kind of recap on some of the key benefits of using our EuroFlood, FloodMap and FloodScore products. Our EuroFlood products include multiple flood sources and return periods, which provide a comprehensive and complete view of all major types of flooding for countries across Europe. The analytical insights we provide support better decision-making around flood risk management by predicting the location and severity of flooding, preventing damage and protecting people, property and assets. We have incorporated the most accurate European-wide high-resolution DTM, the benefits of which include uniformity in the specifications and characteristics between countries. And although local models certainly have value, they often adopt different approaches and cover small areas and are therefore insufficient for fully understanding hazard and underwriting flood risk across entire countries. But our EuroFlood products, however, are created using consistent modelling frameworks, but with localized hydrological methodologies and parameters, which allows us to ensure the highest possible accuracy and precision at very large scales. This allows end users to compare flood risk both within and between different countries throughout the world. And finally, our EuroFlood products are available in a range of formats to align with specific end user requirements and are also supported by detailed technical documentation, so customers are confident in their understanding of the data. We also have continuous product update cycles for future enhancements, including the integration of high precision LiDAR. And change reports are also supplied with each of these updates, which clearly explain any alterations that occur to the hazard and or exposure. Thank you very much for listening.
Thank you very much, Katie. That's a really great presentation and a good overview of our FloodScore. As Will mentioned, there's an opportunity for questions at the end of that. Next, I'm going to pass over to my colleague, Dave Martin. He's going to look at the introduction to climate change modelling. Okay, over to you, Dave.
Thanks, Rob. Can you hear me okay?
Yes, we can, yeah.
Excellent. Brilliant. Okay, cool. Yeah, do you want to just pop on to the next slide? Wonderful. So I'll spare the introductions because I've got quite a few to get through. But okay, so I'm going to talk about climate change modelling and flood for a bit, and it's tricky when we talk about climate change. It's probably a good idea to first think about why. What are some of the questions that we're looking to answer? Now, climate change is, for me at least, is a question of sensitivity. It's a question of trying to understand the uncertainty over the future, and perhaps narrow down what the parameters are relevant to whatever it is we're concerned with, whether that's an insurance portfolio or pipelines to manage, properties to plan. Ultimately, we're answering or trying to answer the question: do I or should I consider changing my strategy to flood risk now because of what might happen in the future. So, the thing with flood is it's inherently a very granular problem. The risk to your neighbour's house can be completely different to the risk to yours. It's probably not, but it can be. So, climate changes and the impact of that how climate change can change the frequency of these sort of things can have impacts on a very fine scale. So we think it's beneficial to model it at that fine scale. So some of the questions we look at, things like, obviously, what's my current flood exposure? Very useful to know, and then the relativity from that. So how can that change in the future? But more specifically, by when? What level of uncertainty are we dealing with? Is that risk change spread out or clustered? Is it something that we could deal with as an organisation by treating somehow a small section of assets, or do we have to actually look, is the risk spread right around the country, and therefore it's more difficult? So answering some of these questions at this stage can be helpful for making decisions on the medium, long and short term. Okay, next. So very quick look at our products themselves. So I don't want to dwell on this slide. I've just a quick mention to say that everything that we build is connected. So the futures data sets are derived from the mapping and the scoring data sets, or at least the same methodology to produce the mapping. So it all feeds through. So basically, a risk rating in one is the same as a risk rating in another. And that can obviously feed through into the CAT model as well. So everything is consistent and built upon one another. And next, Rob. Cool. So let's just think about the UK for a moment. So the UK benefits from a fantastic scientific basis in the UK CP09 and UK CP18 programs, which have generated huge amounts of data and insight into these challenges. Far wider than just flood, of course, but we're interested in certain components. And given that we're dealing with uncertainties here, our approach to climate change modelling has been to provide 3 different pathways. So broadly speaking, we call these high, medium and low for simplicity, but these relate to RCPs. So our high emissions is tied to the 8.5, medium to 6. Low has actually changed in the UK from it used to be 4.5, it's now 2.6 that we tie it to, so closer aligned to the Paris Agreement. And again, the point is, if we're making strategic decisions about something that we're uncertain about in the future, it's helpful to follow a single path and take that sort of more deterministic route. But we feel it's more helpful to follow that route knowing what the upper and lower bounds might actually be. So how bad could it be, even though it's unlikely? Well, how good could it be, although it's unlikely? And that's a theme that we maintain throughout our products. Now, we don't have time to talk about exactly how we get there. There's quite a few decisions to make along the way, how we treat the probabilistic outcomes from climate models, from the UKCP, a little bit too technical for now. Very happy to talk it through with anybody at a later date. But essentially, we define these high, medium and low profiles and then project those into the future. And Rob, next. And this was just, okay, that's supposed to come in nicely. So this is just a zoom in of the previous graph, but this is a matrix of essentially the 9 future scenarios. So when we talk about climate models, we need to talk about points of time in the future, but this is even in itself difficult because you're not really talking about a single point of time in the future. You're talking about a multi-decadal epoch, a chunk of time between now and the future. So to put it another way, the 2020s, these climate models are simulating continually into the future, hour by hour, simulating our weather and other various systems. We basically need to average chunks of that to create what to us now appears closer to a point of time. So the 2020s is basically near term. it actually spans from, in the UK, 2015 to 2039. So several decades of time, and that is averaged out a bit like we average out a flood gauge looking back for 30, 40 years in order to try and explain what's going on now. So essentially we deal with the same type of processes that we use now, but we just imagine that we're in the future and that has just happened. So 2020s, 2050s, 2080s, near-term, mid-term, and long-term risk. High, medium, and low emissions, that gives a nice matrix of 9 that you can follow through in time or follow through in terms of the emission profile and see how that impact can happen. So next one, please, Rob. Okay, so the big challenge that we have from moving from climate data or climate model output to hydraulic flood map output is we have to go via hydrology. So how does the climate model actually change the hydrology or the way that we view that hydrological model in order to change what we then put into the hydraulic model? That's really difficult. And there's a great deal of science that we've consulted in order to get to this point, especially in the UK, where quite a lot of this science was done on the back of the UK CP data when that was first available in 2010, I think it came out after, or 2009. So essentially what we're doing here is we're translating climate model outputs, which might be things like temperature changes or amounts of averages of rainfall, changes in patterns, into more specific things like short duration intense rainfall or things like peak river flow. Most climate models will not touch peak river flow. That's a difficult concept to understand, and is actually dependent on quite a few different factors that come out of the models. That is something that you can't just do, just simplistically. It's very difficult to actually understand how to translate one into the other. So that's where a lot of the work has gone in with the climate modelling projects that we've done in the UK and moving into Europe. So there's lots of different ways of doing that, some far more sophisticated than others. In the UK, we've been very fortunate of using work that's come out of the Centre for Ecology and Hydrology, so CEH, some great work from the EA, NRW, SEPA, UCWIR. A lot of these organisations have produced science that enabled us to then derive these products and these uplifts, as we call them, to our existing products. So this is, just to put it into context, what we see on the screen now are some uplifts, some changes to the fluvial models. So this is the change in peak flow that you will, this is just at the 100-year return period, the change of peak flow from now and into the future under the 3 different scenarios. This is essentially what we need in order to then hydraulically model the output, which then can give us the impact and therefore the full risk equation at the other side. So that's where I'm going to leave it at that. There's tons of information I've left out, of course, but essentially this is what we get. So this is, again, just looking at the 100-year, this is just a baseline for 2017, so essentially the now. Actually, Rob, can you just flick through these ones a little bit quicker? So this is moving into the 2020s, high emissions profile we're following now, and then into the 2080s. You get the idea. Essentially, flows increase for the same event as we go into the future, and they increase more the higher the emissions. If you can keep going, Rob, this is the same for pluvial, a little bit more. So we're jumping into medium emissions, 2050s here, and then we'd make an enormous jump to 2080s, high emissions. This is one of the most extraordinary patches of extreme risk we found. I think it's in Bristol, actually, where the drains were just overwhelmed by that extraordinary event in about 80, 90 years' time. And these are the sort of things that you just wouldn't know without doing those kind of simulations. So that's yeah, something that we're very keen to disseminate. So the next one. So here's just a quick look at the FloodScore product. These headings relate to fluvial, pluvial, tidal, and combined, so F, P, T, and R. I'm not going to dwell on this slide either because, again, it's quite technical, but essentially this is how we derive our products, as Katie went through. For the future products, we use the exact same format and technique, so that it's quite comparable, relative. Of course, they might not go, the risk might not actually go down, it might go up. It might not go up, it might go down in the short term. That's what some of the modelling outputs are showing, depending on which emissions scenario you follow. But essentially, it just makes it easy to relate something in the future to now. And you can look at that with defences turned on or ignoring the presence of defences or whatever. Cool, next slide. So yeah, there's just, we're going to look at, we've got 3 more slides to go. We're just going to look at 3 different ways that you can use the data. Spend about a minute on each. So this is just globally, or not globally, nationally, looking at the whole of Great Britain. The graph on the left is explaining the one in 100-year flood event level, how many properties have some sort of potential impact, and that goes from 1 in 9 today or a couple of years ago. Stays around 1 in 9 as you go into the medium emissions profile. This is into the 2020s, but it increases a bit. We get to about 1 in 7 by the 2050s, and then just about 1 in 6 by the 2080s, which is extraordinary, really, when you think about right now. It's fairly kind of the conventional wisdom, if you like, is that about 1 in 6 properties is some form of risk in the UK. So that's, you know, the 1 in 1,000 year, an order of magnitude less frequent event, more severe event. And this data is suggesting that actually we might be moving to a position where actually that is the norm for the 1 in 100-year event by the end of the century, which is quite startling. But actually, if you look at that in more detail, what you find is much of that is just it's basically the surface water model and very shallow depths. So actually a better way of looking at that is looking at risk, so bringing damage into the equation. So if you go to the next slide, this is how we tend to do it, for example, for insurance companies. So we can imagine these as 2 insurance company portfolios. So what we've done is aggregated the risk in this case. So we've got, you know, risk summarized into 6 bands rather than the 0 to 100. So we just washed it into 0 to 5, by reclassifying it. And this could be an asset manager's portfolio, insurance portfolio, whatever really. And what we're trying to do is say, all right, let's take right now, project it to 2050 under the medium emissions profile. We're going to follow that one. And let's just see what the shape of risk looks like as a pie chart in this case, at that point in time in the future or thereabouts. And what we found is quite interesting. In this case, the 2050s lower risk starting point group, so in other words, the portfolio with relatively low risk now, actually doesn't have that much more risk in the future. I mean, really, it's minimal. We've got maybe 1% that's moved from negligible up to very low or something higher, which is, I mean, that's actually surprisingly low. That's very fortunate. I think in this case, it's probably you'd expect it to be a little bit higher than that on average, but there's some randomness, of course, here. But really, it's quite surprising that very little has changed on the aggregate. If we look at the high risk profile, and again, of course, we've selected for effect here, it won't be the case every time, but this particular high risk profile really does show a significant increase in risk as you move forward. And that we found really quite interesting. Particularly, this is properties moving up into the very high risk profile. And what that tells us is that the impacts of climate change with flood are just not linear, and that justifies, to my mind at least, it's worth going to this level of detail, to the property level, to look at this sort of thing. So yeah, I think there's one final slide before the summary. We move on. This is just again another way of looking at similar sort of thing. This is using average annual loss as the metric. Everything ties together, whether you look at it, the risk ratings are derived from average annual loss. And this just shows all of the different future RCPs on the same graph, so you can kind of see which flood sources are more certain and which are less certain, which in itself can give you more kind of richness of data to play with and get confidence one way or another in your mind. Because ultimately this is an uncertain thing, and we're trying to just build as much knowledge around what might be as possible. So final slide, and I'll leave it there. This is just a few benefits around why we've done it this way, and why we based it on our FloodScore insurance offering. And really that's just to make it easy to work with, because not everyone wants to answer the same questions, and not everyone wants to go to the nth degree of detail. But crucially, there is a massive repository of data here that can be used to answer lots of different questions, and the answers it will give can be very, very simple and very, very clear. And that's it. I'm going to leave it there.
Okay, thank you very much, David. That was a really excellent presentation, and looking at really climate change flooding in the future. It's quite scary what it actually shows in the UK and Europe. Now I'm going to hand over to Rubini, and she's going to go through the CAT modelling and focus mainly on the Australian models. Over to you, Rubini.
Thank you, Rob. Thank you, Dave. Can we just switch on to the next slide, please?
Yeah.
So my colleagues, Katie and Dave, spoke about the production of flood map and FloodFutures and things and its key features. So in the next few slides, I will be talking about how the FloodScore, especially the property level FloodScore risk rating, is used in the development of FloodCat, and most importantly, how the changes in the production of the FloodScore, that is the risk rating database, impacts the FloodCat results. So here's a slide which tells us like how the FloodScore and the flood map ties into the development of FloodCat. This is just an introductory slide. Can we move on to the next slide, please, Tom? Right, before we head on to the development of FloodCat, I would just like to touch base about the deterministic and probabilistic modeling. So most of you, as you know, deterministic model is meant to yield a single solution describing the outcome of an experiment given appropriate inputs, whereas a probabilistic model is instead meant to give a distribution of possible outcomes. That is, it describes all outcomes and gives some measures of how likely each event is likely to occur. So in a nutshell, a deterministic model does not include randomness at all. Every time we run the model, we get the same exact results with the same initial conditions. But when a probabilistic one, we will give different results each time we run with the same initial conditions. So these are the basics of how we are going to deal with the further slides going forward. Next slide, please. Right, so here are the principal components of CAT model. And before that, what is a CAT model? So the commonly accepted definition for a CAT model is it is a computerized simulations that use scientifically derived physical models to estimate where a catastrophe event will occur and how severe they will be and how much damage they will cause to properties. And most importantly, as we all care about what financial consequences will it produce to the stakeholders. So this is the most accepted and simplest definition for a CAT model. And here are the components which actually go into a CAT model. The first main component is a hazard model. The second one is the vulnerability. And the third one is the financial module. So there are two subcomponents in our hazard one, which is the event module and the local intensity calculation. I will quickly touch base on all these simple components before we get into the actual discussion. So in case of event module, it is just its data. I wouldn't say it is just, yeah, it is database of stochastic events. So it is usually created using the past events and also stochastically simulated events that may not have occurred in the past. So just like it inclusive of the FloodFuture components, what Dave just spoke. So, and for each event in the set, its physical parameters such as location and annual probability are defined. So the next one is the crucial thing, which is the location intensity calculation, where our hazard map components, which my colleague Katie spoke about. So in this case, where the local intensity calculation comes, for each simulated event, the intensity of the hazard is calculated at each affected site. So in short, I would define this as hazard as a consequence of the event that caused the damage. And the next part for the hazard component itself is the it's not technically inside the hazard component, but it is directly linked to the hazard one, which is the exposure data. So exposure data is the information about the property, which includes physical characteristics, replacement value, and so on. So in this case, for this case study, it would be Australia, and there we use the which is represented as GNAF, which is the geocoded national address file, which has the latitude and longitude information and all other information what I mentioned previously. These two components feed into the main another module, which is the vulnerability one. So where the damage estimation happens. So the damage estimation where the physical damage is calculated for each affected exposure. Going forward, in case of the damage estimation component where the vulnerability is the key, the vulnerability function it completely varies for each building. For instance, it will change in the basics of the various building characteristics, such as construction type or age of the building or the height and occupancy type and so on. We will discuss about how this vulnerability actually influences the CAT model results in maybe after 4 or 5 slides from now. Last but not the least, all these things tie into the expected result, which is the loss estimation. So in the loss estimation, this is a stage which converts the damage ratio from the vulnerability module into financial loss. The damage ratio function for the specific event is multiplied with the building replacement value, which is usually known from the engineering codes, and which gives us 2 different components, 2 different outcomes, which are the AALs and EP curves. We will discuss about what these outcomes are through the end of the slide deck. Next slide, please. Right, so we talked about what is a CAT model and what are the components which go into building a CAT model. Although we haven't discussed what are the outcomes of the CAT model, which we will keep the placeholder now. So what does Ambiental Australia Flood CAT offers? So I've mentioned about the key benefits here, and mainly I want to focus on the model features. So in the previous slide, we did see about the importance of hazard and the property and the exposure, because these two are the main ingredients which is going to impact the results for the loss financial loss estimation. So in case of hazard, so we have, Katie has covered all these things, but I just want to reiterate this again. So we have a full countrywide model for Australia, and for the hazard production, it is based on 2,000 and odd flow gauges and 1,000 and odd rain gauges. And for the synthetic database, for when we are predicting the event sets, which are stochastic, here we have about 10,000 synthetic years and over 50,000 events. And coming to the exposure data, we have high precision LiDAR for major cities and urban areas. Why is this important? Why am I reiterating on having high precision LiDAR for major cities? We will answer this by end of the slide deck. That's going to be the major discussion for this piece. And last but not the least, the vulnerability data representing multiple building types. Thank you, Rob. No, you were right. You were spot on time. So here's what the input data for the hazard and for the exposure data goes into. So we have the coverage status as of 2020, we have 80% of all the properties is covered by LiDAR. The blue color represents the urban model, and the gray one goes for the rural one. So this is just a pictorial representation of what we have in there. Next slide, please. Right, so we talked about what CAT model is, so it was more technical, and then we talked about how Australia CAT model, Flood CAT looks, Ambiental's Flood CAT looks like. But this is more of, so I just wanted to give you a pictorial representation of how an event looks like, because for the non-CAT modelers, I just wanted to give you like a feel of how an event looks. So to your left, what you have is a probabilistic event. So it is represented in blue. Whatever is represented in blue, it is the low written period, and whatever is in red is all high written period. So in the view of time, I would just like to go to the next slide. This is all just a pictorial representation of what I spoke, so we're not missing anything. Now, how do insurers actually use the CAT model? So this is a classic example. So what I did was we ran a portfolio which has about like 10 properties, and one portfolio has a high set, what you see on your left, the topmost image, and another one with the low set. So a logic here is met, because when a same flood happens, the low set property is likely to suffer more loss compared to the high set property. So this is a classic example which tells why it is very important to have the primary modifiers such as like elevation into your exposure database. So the more detailed your exposure database is, the more your results are more reliable. Next slide, please. Right, I actually missed to say something about in the previous slide about the outcomes of, which I promised, the outcomes of the CAT model are usually, sorry. So the outcomes of the CAT model are usually two things. One is the EP curves, which the practitioners usually call it as exceedance probability. It is a probability exceeding a specified loss threshold. And what you see here is this metric, which is commonly accepted, which is the average annual loss. This is an expected amount of loss from all the events in a given year. So we have 10,000 synthetic events and about 10,000 event years and 50,000 events. So when we calculate the amount of loss from all these events in a year, you get the AL. So this is a metric which is commonly used commonly used for a CAT model. Next slide, please. So Katie and Dave and we all talked about how important it is to have the property level detail models in our products. So this is a classic example where I want to this is a picture where I just wanted to focus for a minute, which says like, the circle with the dot shows the exposure data set, which is a building centroid, and its 15-meter buffer is shown with the dotted circle. The risks, so you here in this image, we have like actually two databases. The one database is one with the dot and a circle, another one is a polygon. So the risk score is based on the buffer shown in a dotted line for database 1, or we can call it as FloodScore 1. And for the FloodScore 2 was derived on the polygons you see, which is the actual building outline, which represents the true shape of the building. So we compared these two data sets, and Rob, next slide, please, which has the results actually. So when the risk scores were compared between these two data sets and the delta was plotted and color coded, we noticed some interesting results. So let us just focus on the box area here. There is moderate to very large reduction in the risk rating when we use the building outline. So the green one, the light green to dark green, it showed like there is moderate to very large reduction in the risk rating. So what is causing these three? This reduction, or this delta? So the three principal reasons were location, shape, and area. So why is location deriving this change? In urban areas, there is good correlation between standard address point and the building footprint. So we don't really want to worry too much about that. But in case of the rural one, the points can be quite far from the building location. So if the point is not actually in the building location, that means it is not truly representing the risk in that given area. Secondly, when even in the urban area, if the GNAVs points are rightly placed within the building, they're often placed close to an edge. We will actually see that how that actually influences the risk rating the next slide, but not right away. Because in the waterfront property, structures are located in the most elevated position within the land parcel, which are well captured by the building outlines, but not by the centroid points. So I want to skip through the shape and area because the most important thing is the location. So that's how location actually influences your risk rating, which is why we reiterate on having property level database for your risk score. Next slide, please. So this is a classic example. If you look at this one, this building polygon, if your centroid was placed towards the left, it would definitely be missing the actual risk score. So this is the reason why we advocate having a building outline, because this captures the right risk from the building, from the flood line. Next slide, please. Right, so this is the case. So we compared about 1.5 million records between FloodCat 1, which was produced from building points, and FloodCat 2, which was building from building outline. So when we compared these two, there was about 10% of risk reduction. This would, well, we are still validating our results, but we can conveniently say that using building outlines is having an impact over your overall AALs. Next slide, please. So here's a slide which talks about our salient features of how we have implemented our FloodCat, and I did mention about producing comparing two different FloodCats. So this means like we have refined our rapid development, and we have automated most of our steps in our FloodCat production. Next slide, please. So here's the platform where we have deployed our floodcat models. So one is the Oasis, which I'm sure all of you all know, and the other one is impact forecasting, which is the Elements. Thank you very much.
Excellent. Thank you very much, Robini, Katie, and Dave. That's 3 excellent presentations now. Just to wrap up before we go to questions. I think, as Katie and everybody said, insurers will expect more for their flood models. We're finding this more and more. And I think with the future of climate change and other sort of improvements in data, insurers and other financial sort of institutions are going to expect more across their flood models, high resolution, quality of the data across Europe and globally. We're also experiencing very much on the climate change. It's quite early days still, but we're finding that utility companies, local governments, insurers and others are all starting to look at climate change, particularly when they have assets which they want to sort of assess in the future. And as Dave said, some of the issues and some of the models actually strike up a massive increase in particularly pluvial flooding and others in the future, 30 to 50 years ahead. With the CAT models, we're really sort of innovating that very much in the marketplace with Australia, and we're looking to develop other models as well, and how we innovate and how we sort of build those models going forward.
We had a question, I think it's directed at David or Katie, asking how defensible the rainfall discharge for a 10,000 year return period event was.
So yeah, it's a really important question because it clearly is highly uncertain at that level, hydrologically speaking. Clearly, we've got nowhere near a 10,000 year record to use to predict the future, whether that's climate change or current present day, whatever we're doing. It's very, very uncertain. What I would say is defensible is the reason that we do it, rather than specifically, I'll come to that in a second. I mean, basically, the reason we need it is for CAT models. Generally, for a full catastrophe model event set, you will simulate 10,000 years of synthetic weather. That's the kind of industry standard minimum for the number of synthetic years of rain, of events, of weather. So within that time, you would probably expect 10 or so, or just under, events to exceed that 1 in 1,000 year return period at certain locations across the country. So essentially, if you don't have anything beyond the 1 in 1,000 year, which is generally the highest you'll see in on planning, for example, the Environment Agency planning websites, which in itself is still pretty uncertain, of course, but nothing like obviously 10 times that. If you don't have anything beyond that, then you're essentially guaranteeing that you'll understate those risks. So these ultra rare events are ultra rare, but you should, in order to be able to capture the impact that they could theoretically, and we don't obviously experience them very much, occur, we need to have something beyond that level. So that's why we simulate the 10,000 year. It actually barely factors into the insurance risk ratings or the average annual losses because it's too rare. So when you look at the probability side of the equation, it's so low that it can't generate a 1 out of 100 by itself. It will flag it as flood exposed, but it needs to be combined with some other logic to actually get onto that scale.
David, I think we've got another question for you from Taiwo, asking what software you use in doing your analysis for the flood mapping. What's the methodology and source of data? So
the hydrology is unique to the country. That's one thing we're very keen on. So if we're modelling Spain, we want to use Spanish hydrological methods. If we're modelling Australia, we use Australian hydrological methods. In the UK, again, UK hydrological methods or data. Basically, local knowledge tends to be really beneficial when you look at hydrology because if you've been living somewhere and experiencing these things for a long time, then clearly the engineering manuals are likely to capture that. So that's on the hydrology side. So that varies, and that could be from Excel models to more sophisticated hydrological packages. But On the hydraulic modeling, we use our own proprietary system called FlowRoute, which is a two-dimensional flood model, similar to something like ListFlood or TwoFlow. Basically moves water along. In the UK, in Europe, all of our models are 5-meter hydraulic models, so it has to run very quickly. And we're spinning up, put it into context, the UK has more than 1 million hydraulic flood models simulated. So it's something we have to use our own tools because we need to script them on a massive scale and apply them to supercomputers. Yeah, there's so much. I mean, maybe one of the product documents would be a good place to talk about some of the sources of data and so on.
The last question, for the Australia CAT model, are the 50,000 synthetic events validated against historical flood outlines?
Yes, we do have few of the synthetic events. Yes, few of the synthetic events have been validated against the past events. I mean, that's the way to go forward. Yeah.
We have just about all the major flood events in the model as well, which is one way to make sure that your calibration is accurate, because that will test the vulnerability components as well as the hazard components.
I just want to thank everyone for giving your time talking today. It's an extremely interesting set of tools and a set that I think everyone attending can use to support better decision making around flood risk management. So I've posted the link to the tools in the chat now. Just a little bit from Oasis Hub. We're the global window to free and commercial environmental catastrophe risk data tools and services. We're here to help you find the type of tool that you need. If you're interested in this set of tools or any other tool that you find in Oasis Hub, email us at hello@oasishub.co and we'll be in touch. The next webinar is in a fortnight on the 19th of October. Dr. Avi Baruch, who's the COO at Provisico, will present their flood forecasting technology, demonstrating how that tool has helped insurers and the government mitigate flood impacts this summer. He is also going to reflect on Provisico's work transforming flood underwriting and claims processes. So we invite those working in the insurance industry, businesses, and in municipalities seeking property level flood warnings to register at oasishub.co. So thanks everyone. Please join us again.